Greenland has lost nearly 5 trillion tons of ice since 2002. That is enough weight to shake the very crust beneath it. As the land rebounds, dormant faults are reawakening, and small earthquakes are being triggered in a landscape once thought geologically silent. Scientists tracking these shifts are uncovering consequences that reach far beyond melting ice. Why is Greenland's ground trembling now, and what does it reveal about the planet's future? Across the Arctic, Greenland stands out as a continent-sized reservoir of ancient ice. Its frozen cap stretches over 1.7 million square kilometers, an expanse large enough to blanket nearly a quarter of the continental United States. But this immense shield is thinning at a pace that defies historical precedent. Since 2002, satellite missions from NASA and the European Space Agency have tracked the gravity around Greenland, effectively weighing the island from orbit. The numbers are staggering. Nearly 5 trillion tons of ice have vanished in just over 2 decades. That is enough water to cover the entire state of California with more than 12 meters of meltwater, or to raise global sea levels by over 1 centimeter. Every year the loss continues. In recent years, Greenland has been shedding between 270 and 400 billion tons of ice each year. That is more mass than all the living humans on Earth, lost every year as meltwater drains into the Atlantic. The pace is not steady. About 40% of Greenland's annual ice loss now occurs during short, extreme melt events. These heat waves have become twice as common and twice as intense since the 1950s, turning what was once a slow trickle into powerful surges of runoff. The GRACE satellites detect these changes not by looking at the surface, but by measuring minute shifts in Earth's gravity field. When ice disappears, the planet's gravity weakens in that location, revealing the scale of mass loss in real time. The data show a clear trend. Greenland's weight is dropping and the rate is accelerating. In southeast Greenland, the ground beneath the shrinking ice is rising by up to 4 centimeters each year, as if the land itself is trying to rebound from centuries of compression. This is not just a story of melting ice. Removing trillions of tons from Greenland's surface is like lifting the lid off a giant geological spring. The crust, once pushed down by the sheer mass of ice, is now shifting upward and setting off a cascade of physical responses deep within the Earth. The next question is what happens when that much pressure is suddenly released, and how the ground beneath Greenland reacts to losing its ancient burden. When the weight of Greenland's ice is peeled away, the ground beneath does not simply stand still. It begins to rise, a process known to geologists as isostatic rebound. The idea is straightforward. Imagine a wooden board floating in water with a heavy stone on top. Remove the stone and the board springs upward, seeking a new balance. Greenland's crust, pressed down by kilometers of ancient ice, responds in much the same way when that ice melts away. Except here the spring is the slow, powerful flow of the Earth's mantle, pushing the land back up over years and decades. But this rebound is not just a gentle lift. As the crust flexes and rises, it redistributes stress deep within the bedrock. The rocks beneath Greenland are laced with faults, some dating back a billion years. Many of these faults have lain dormant, locked tight under the crushing weight of the ice. Now, as that load is released, the clamps loosen. Old weaknesses become zones where the shifting pressures can finally break through. This process is different from the earthquakes that strike along the boundaries of tectonic plates. In places like California or Japan, quakes happen as plates grind past each other. In Greenland, the story is one of adjustment. These are not the violent ruptures of colliding continents, but the slow, persistent response of a landscape returning to equilibrium as its burden disappears. Scientists call these adjustment earthquakes, events triggered by the changing weight above, not by the movement of plates below. Researchers at the Geological Survey of Denmark and Greenland, called GEUS, have become interpreters of this hidden drama. By combining satellite data, GPS readings, and seismic records, they can track how the crust flexes and where stress accumulates. Their work reveals that as Greenland's ice thins, the land does not just rebound, it can also reactivate ancient faults, sometimes producing earthquakes in places that were quiet for thousands of years. Understanding this mechanism is key. It means that with each surge of melting, scientists can anticipate not just rising land, but the possibility of seismic signals, evidence that the Earth itself is responding, deep below the surface to the loss of Greenland's ice. Seismic stations now ring the Greenland coast, quietly recording every tremor and shift. The Greenland Ice Sheet Monitoring Network, GLISN, has transformed what scientists can see beneath the ice. Since its full rollout in 2013, GLISN's more than 30 broadband sensors have captured a steady drumbeat of earthquakes, some no stronger than the rumble of a passing truck, others reaching magnitude 4 or higher. Alongside these seismic readings, a network of GPS receivers keeps a constant watch on the ground's vertical motion. In southeast Greenland, the crust is rising by as much as 4 centimeters each year, an astonishing pace for solid rock. Even in the west and northwest, uplift rates routinely reach 2 to 3 centimeters annually. These numbers are not theoretical. They come from daily measurements, with time series showing a staircase pattern, each summer melt season kicking the land upward in sharp steps. Uplift is happening in measurable, repeated pulses. The link between melt and motion is sometimes stark. On August 13, 2017, an earthquake of magnitude 4.1 struck near Qaanaaq in northwest Greenland. That same week, satellites documented one of the most intense local melt pulses in recent memory. Surface meltwater pooled across the ice sheet, and GPS stations in the region recorded a spike in uplift. While scientists stopped short of declaring a direct trigger, the timing is hard to ignore. A peak in surface melt, rapid unloading of ice, then a sudden slip along an ancient fault. Events like the Qaanaaq quake have become a focal point for researchers who are piecing together the sequence of melting, uplift, and seismic response. Across the island, GLISN data reveal a clear pattern. Earthquake rates climb during melt season, especially in years of extreme runoff. The quakes are small, but their frequency is rising. This is not just a story of ice and water, but of deep earth mechanics, of crust lifting, faults awakening, and the entire system responding in real time to the loss of Greenland's ancient ice. The crust beneath Greenland still bears the imprint of the last glacial maximum, when ice up to 3 kilometers thick pressed the land downward by as much as 2 kilometers. That ancient weight left behind a crust riddled with old faults and weak zones, features that now respond to even modest changes in stress. In the present era, the scale and speed of ice loss are testing this system in ways not seen since the end of the Ice Age. One of the most striking examples came in July 2019, when Jakobshavn Glacier, already one of the fastest flowing in the world, suddenly accelerated by 10 to 20% during a single extreme melt week. Alongside the surge in ice speed, a cluster of small earthquakes rippled through the bedrock. Scientists are still debating whether these tremors were driven more by meltwater lubricating the glacier's base or by the rapid unloading of ice shifting the crust. Either way, the event exposed how closely ice dynamics and seismic signals can track each other, and how quickly Greenland's system can respond to surface changes. Recent seismic surveys have added a new layer to this picture. In 2025, researchers using passive seismic imaging revealed that soft, deformable sediments are far more widespread beneath the ice than previously thought. These weak layers act like a lubricated cushion, amplifying the glacier's response to meltwater and potentially making some regions much more sensitive to future warming. While there is no single number for how much this could increase ice loss, the implication is clear. Greenland's vulnerability is greater than many models have assumed. This sensitivity is not unique to Greenland. In Antarctica, the Thwaites Glacier region has registered hundreds of glacial earthquakes in just over a decade, events linked not to shifting tectonic plates, but to the dynamic interplay of ice, water, and underlying sediments. Studies show that when sediment-rich beds become saturated, ice flow can accelerate dramatically. These findings have forced scientists to adjust global sea level projections, sometimes shifting model outcomes by 10 to 20%. All of this points to a system where small earthquakes are not just background noise, but signals of deeper feedbacks, where the solid Earth, the ice sheet, and the ocean are locked in a tightly coupled experiment that is still unfolding. Greenland's shifting ground is proof. Climate change now moves the very bones of our planet. As ice vanishes, the Earth itself reacts, faster than science once believed possible. These tremors warn us. The consequences are not distant, they are unfolding in real time beneath our feet.